A very common desire when controlling a motor is to actually be able to control the speed of that motor, right? And we have, knowing our kind of speed torque characteristics of a particular motor, we know we can pick a point, for example, somewhere on this curve that gives us a particular speed and a particular torque, right? But if I have some kind of mechanical load on my motor that I'm trying to drive, that torque that I'm trying to provide is going to be fixed. So I don't necessarily want to move along this curve. I just want to move up and down right here. And if you remember, we can control the kind of designation of this line right here by changing the motor supply of my motor. So I can kind of continually move this down like this by changing that input voltage to my motor. So now I could have that same torque that I'm trying to drive, but I could drive that at 3 different speeds right here. So omega 1, omega 2, and omega 3, based on these 3 different input voltages to my motor. So what this is telling me is that not only do I want a way to be able to turn this motor on and off, I want to be able to make this motor speed variable up here. And so the big question is how I can actually do that in a fairly simple way. So we're going to accomplish this by using our ability to turn the motor on and off. So in this case, I have a PWM signal, a pulse width modulated signal. Here I'm trying to draw something with a duty cycle of approximately 50%, which means that it's on 50% of the time. And if I have appropriate filtering here, so say this is my V motor that I'm switching between that, then the resulting signal, kind of approximate voltage that I'd get out of this would be half of that motor voltage, right? Or my duty cycle times the motor voltage. So similarly, if I had a signal that was on only 25% of the time, in that case I'd get an approximate voltage on my motor that's about 25% of my V motor. So if I had a 12 volt supply for my motor and this PWM signal, assuming the frequency and everything is good based on my time constants, then I would get effectively a 3 volt input to my motor, right? And this is very approximate as well. Okay, so the other thing to consider is that PWM frequency, which is 1 over the period. And if I don't want some obvious stopping and starting to my motor, right? So if this was very slow, say my period was something like 10 seconds, right? So I turn it on for 5 seconds, I turn it off for 5 seconds. I guarantee you'll see the motor accelerating and decelerating in that time frame, right? And the motor is controlled, right? We're going to use the idea of filtering. I need filtering in order to get this approximation. So my time constants that are going to provide that filtering are both the mechanical time constant associated with the motor, so based on that inertia that I'm trying to drive with the motor, as well as the inductance in the motors providing an electrical time constant, right? And tau in that case is L over R for an inductor. Right, so I'm going to have to make sure that this frequency is such that I'm at a higher frequency, or my period is smaller than those time constants, so that I don't get appreciable kind of turning on, turning off behavior. And typically, you can use a fairly wide range of frequencies for most of the motors that you'd encounter. So something at a couple hundred hertz would probably be sufficient, all the way up to tens of kilohertz. But the effect of this is a really big approximation right here for this approximate voltage that we're applying to our motor. We will get a very nonlinear curve between the duty cycle and that speed that I'd ultimately get out of my motor. So a typical curve that you might see between duty cycle and speed at a fairly low PWM frequency is something like this, right? So I'm going to hit my max speed up here at my 100% duty cycle, so I'm constantly on, right? And that would be the speed correlating to my V motor up there, right? And then based on the load torque that I have. But I get this really crazy behavior at the beginning, right? And it's definitely very nonlinear. So this would be at a fairly low PWM frequency, right? And this point down here, right, is going to be due to friction torque in the motor. So if my PWM frequency, or my duty cycle, is too small, I never get enough current through that to actually get the motor started. All right, if I have a higher PWM frequency, that will move up a little bit, so I need even a higher duty cycle to get things started, but it starts to flatten out and become a little more linear there. And if I have an even higher duty cycle, it actually looks very linear, but still starting at that 20% duty cycle. So that's at a very high PWM frequency. And that will, once again, the actual magnitude of that frequency is going to depend on the actual mechanical situation that I'm in, so the kind of inertia and torque that I'm trying to provide with my motor, as well as the motor design itself, so the inductance and resistance in that motor, effectively the time constants that I have to deal with in my system. So regardless of that PWM frequency, though, I am still going to get some ripple in the current that I'm applying to the motor. So when I make the motor voltage high, right, my current is going to increase a little bit, and when I turn it back down to 0, my current is going to decrease. And these are, remember, related to the time constants of the motor, specifically that inductance, tau is L over R. Typically that will be the dominant time constant. If you're operating at very low frequencies, the mechanical time constant might be dominant, but at higher frequencies, this L over R will be dominant. And so if I'm looking at this orange line here as my I motor, I have some maximum and some minimum current that I have going through there. And remember also that my torque is going to be proportional to that motor current, so I'm going to get some torque ripple that's proportional to that current ripple in my system. And I want to operate this fast enough, so if I have a higher PWM frequency, I'll compress this ripple and I'll operate at a much lower torque ripple, which, depending on my particular application, I might want to make this very small, or I might be willing to deal with a reasonably high torque ripple in my system.